Okay, everybody. Welcome to chapter 14, part A. This is going to be the lecture on correlation, which I'm actually really excited about. Correlation is a really, really neat part of statistics. So I hope you guys might enjoy this also. Oops. Okay, sorry about that. We're having technical difficulties tonight. So after this chapter or lecture, you should be able to understand Pearson's R as one way of measuring how variables are related. You should be able to compute it using two different formulas. You should be able to use and interpret it, understand what it means, basically, test a hypothesis using a sample R, and understand the concept of partial correlation, explain the Spearman correlation coefficient, the point biserial correlation coefficient, and the phi coefficient for two dichotomous variables. So all kinds of things we're going to cover today. Um, I'm going to plant my extra credit lecture listening question right away this evening. I, of course, encourage you to watch this entire lecture video. I intend for it to be extremely helpful to you. But if you are just doing this for extra credit, here you are. I had pizza for dinner this evening, and the extra credit question is, what is my favorite pizza? Um, this is a little bit lame. I really like, there's a Chicago deep dish pizza that I love, but when that's not available to me, the answer to the question is Pizza Hut thin crust pepperoni pizza. Lame, but true. Okay, so here we go. Let's see, a couple of years ago, there was an NPR study about people who shop with reusable grocery bags. And the study found that people who shop with reusable bags are more likely to spend more money on organic food compared with those who shop with disposable bags. Maybe not that surprising, right? You would think people with reusable grocery bags buy a lot of organic food. But the study also found that those same people are also more likely to spend more money on junk food. And that might be a little bit more surprising. So, how could we use what we've already learned in statistics this semester to test whether people who shop with reusable bags spend more on junk food than people who shop with disposable bags? I'll just give you a second to think about that. Um, and then I'm going to point out and ask you kind of to step back and remember to the very beginning of the semester. The inferential statistics that we've learned about so far are about group differences, right? So remember, first of all, inferential statistics meaning using a sample and collecting some information about that sample and using that information to make inferences about a population, right? So we're not realistically going to measure the entire population most times. And so we use inferential statistics to try to make some educated guesses about the populations from samples. And thus far, all of the statistics we've talked about are measuring differences between groups, right? So one thing we could do with perhaps a t-test, for example, an independent samples t-test, is look at whether people who shop with reusable bags spend more on junk food than people who shop with disposable bags, right? So we've got an independent variable, what kind of bag do they use? And our dependent variable would be spending money on junk food or amount of money spent, perhaps. And we could do a pretty simple independent samples t-test to see whether there's a difference between those two averages, right? Or sample means. But An equally interesting research question might be asked about the relationship among variables. So you might want to know, among people who shop with reusable grocery bags, is there a relationship between the amount of money they spend on organic food and the amount of money they spend on junk food? So here we're not comparing two different groups of people. We're looking at how much do they spend on organic food and how much do they spend on junk food? What's the relationship there, right? If somebody spends a lot on organic food, do they also spend a lot on junk food? Do they just buy a lot of food in general? Or is that not necessarily the case? And so that sort of question, where you're looking at relationships versus differences among groups, would be examined using correlation. So correlation is a technique that allows us to measure and describe a relation or relationships among two or more variables. It requires at least 2 scores from each participant, and usually participant variables are observed, not controlled or manipulated. So meaning, with a correlation, there is no manipulation done. We usually are just observing and measuring variables as they exist naturally in the environment. So one example, participant variables could be grades and family income. So um, I'm not going to attempt in a correlation study to manipulate grades or family income. I'm just going to measure them as they are and examine, is there any relationship between grades and a family income, for example. So the no manipulation part is important. Later, we'll talk about this in terms of correlation not equaling causation. And you may have heard that before. It's very important. And like I said, we'll come back to that concept. But just briefly, here's some important points about correlation. So you might ask, wait a second, how is this different again from t-tests or ANOVAs that we've been doing? And remember, like what I was just saying on this previous slide, t-tests and ANOVAs look at group differences, where correlations look at relationships. So to talk a little bit more about that, the only kind of t-test that maybe would be similar to correlations is a related or paired samples t-test. So you'll notice here, when we talked about repeated measures or within subjects designs, related or paired samples t-test, we talked about measuring the same variable twice rather than two different variables. So personality traits measured over time, right? We might measure personality trait. I'm just trying to think of an example here. Conscientiousness, right? How conscientious is someone, and does that change over time or after a particular intervention has occurred? Does something make people more conscientious? Or a measure of social abilities before and after a social skills intervention. So again, measuring the same variable at two different time points, right? Relationship satisfaction, this last example, before and after positive image pairing, right? And again, does that change? So correlation is different from all of these examples listed here in that we are going to examine a relationship among two variables, not a change over time or not looking at before and after a treatment. And it's important, again, to recognize that correlation does not involve experimental manipulation. So several of these, if not all of them, do involve experimental manipulation. I guess the concussion one would not, right? Because we're not going to concuss people on purpose, but um, you know, the relationship satisfaction example is an experiment where you're showing people neutral images or positive images and then measuring, does it have any effect on relationship satisfaction? There's experimental manipulation going on and you're looking at one variable, relationship satisfaction. Okay. Oops, I'm sorry. So again, correlation is a technique that allows us to measure and describe a relationship among two or more variables. You certainly can measure correlations among many, many variables at once. For this class, we're just going to focus on measuring two variables, but it does not need to be limited to two. Just for our purposes, that's what we're going to do. A correlation does require at least two scores from each participant, an X and a Y, which this will become a little bit more clear in just a moment. And again, these variables are usually observed, not controlled or manipulated. And one cool thing is that these scores can be represented by a point on a scatter plot. So here is a scatter plot, and scatter plots are important for correlational data. This scatter plot and correlation is showing the relationship between family income, plotted here on the x-axis, and student grades, plotted on the y-axis. And here we have a sample of 14 high school students. The scores are listed in order from lowest to highest, family income, and are shown in a scatter plot. So here, let's just take 1 point here. So person A, family income, and you'll notice this is in units of $1,000, is 31, and the average grade there would be 72. So that's probably this first dot right here. It's around 31 in terms of income and 72 in terms of grade. And so each one of those 14 people are plotted here with a dot. And what we are going to begin to look for is a pattern in this scatter plot. And I don't know if you guys can see here, do you see any sort of pattern? And by the end of this lecture, you should be able to go back and watch this slide again and say, oh yes, clearly I do. At the moment, you might think they just look a bit scattered around. So there are ways to describe a relationship between two variables, and we're going to be looking at 3 particular ways, and especially looking at a scatter plot of a relationship between two variables. The first way to describe the relationship is in terms of direction, and here we mean either positive or negative. When you have a positive relationship, that means that the change is in the same direction. In other words, as one variable increases, the other variable also increases. That's a positive relationship, and that's shown here on the left scatter plot. A positive linear relationship between hours of study and test scores. So the scatter plot should look like this, where the dots go in a direction from lower left to upper right. The other direction is negative, and a negative relationship simply means that as one variable increases, the other decreases. So they move in opposite directions of each other. Here on the right-hand side here, we have an example of a negative linear relationship. So as the hours of TV time per day increase, as they get higher from left to right, you'll see that the test scores decrease. And so a negative relationship is going to have, basically, when you graph it, it would go from top left to bottom right. If that's the pattern of your scatter plot, then you're looking at a negative relationship. And you can pick a point and kind of talk your way through that, right? So here, this dot on the lower right means about 8 hours of TV time per day, and the test score is around 30 or lower, right? Versus 1 hour per day, the test score is closer to 100. And so you can see as the hours of TV go down, the test scores go up. So when one variable goes up and the other goes down, that's a negative relationship. If they both go up or they both go down together, that's a positive relationship. So that's important to note. As you heard me say, they both go down together. So they can both, um, here in this example, the hours of study time per day, as the hours get lower, the test scores also get lower. And that might sound like I'm talking about something negative, but since they're both going in the same direction, that is a positive relationship. Another way to describe the relationship between two variables is in terms of the strength or the degree of the relationship. So, how predictable or consistent is each value given the other value? And you might use words like weak, moderate, or strong. And so, in looking at strength, we can look at these examples here. These are examples of different values for linear correlations. So in graph A, we have what is known as a perfect negative correlation, right? For every one change in X going from left to right, you have one change in Y. It goes down 1 unit, right? So you could say the slope of this line is at 1, right? If as the X value decreases 1 unit left to right, the Y value decreases 1 unit top to bottom. This would be a strong correlation. In B, there is no linear trend. So we draw a circle around, we clearly can't draw a line through these dots. And when you draw a circle around them, you get quite a round circle. It's not a football shape at all. There is no linear trend. In C, figure C, we have a strong positive relationship because when we draw a circle, or your textbook calls it an envelope, around these points, we see basically a football shape. And since this football is pointed or angled in this direction, is it positive or negative? And you should hopefully review the previous slide if you need to. This is a positive relationship in graph C. And it's a pretty strong positive relationship. It's not perfect, like in figure A, where all of the points fall exactly on a line, but that's highly unlikely in real world research. Figure C is a good example of what you'll see in the real world as a pretty strong relationship. And then figure D is a relatively weak negative relationship. So you'll see it's a little more flat than the B graph, but definitely not quite as football shaped or as flat as the C graph. So it's a relatively weak correlation. This is not super strong. The closer the points come to a line, the stronger the relationship is, okay? And this in figure D or graph D would be a negative relationship because of the way that the scatter plot is angled. And then the third way to describe a relationship between two variables is in terms of form. So scatter plots are really great for helping us see this particular way of describing a relationship, because you could, when you do your calculations and you use the formula that we'll talk about, you could get a very weak or no linear correlation, and you might conclude that the variables are not related, right? If you get a value that tells you there's no correlation or a very weak correlation, and that's because the correlation that we're going to talk about measures linear relationships only. And a linear relationship or correlation is one where the variables uh, are best represented by a straight line. And there are other types of relationships, however, that are non-linear. And one example is a curvilinear relationship. And that's what this graph is showing here. You can kind of see there's these dots in the scatter plot are kind of forming a rainbow shape. And so a rainbow shape or curve is going to represent a curvilinear relationship. Um, if you just took half of the rainbow, you might see a linear relationship, right? Where the change in one variable, anxiety level, corresponds to a particular change in another variable, test scores. And you can begin to draw a line, a non-curved line through the data points. But when you look at all of the data points and you get a curve, that's a different form. And in our class, we are only going to be looking at and measuring linear correlations or linear relationships. So, like I said, scatter plots are a good first step in understanding the relationship, but we do need a statistical measure to quantify it, right? We can't simply plot data points on a graph or scatter plot and talk about correlations. We do want numbers, concrete numbers and calculations to more accurately measure a relationship. And the Pearson correlation measures the strength and the direction of a linear relationship between two variables that are measured on an interval or ratio scale. You might want to go back to one of the very earliest chapters of the textbook in our class to review interval and ratio scales. I'm not going to do that here just in the interest of saving some time. But recall that in those two scales, you can definitely measure the difference between one unit and the next. It's not just understanding an order or rank order. There is a measurable difference, right? And that's just an important thing to know and remember and keep in the back of your mind. So Pearson correlation is not appropriate for ordinal scale of measurement. In a population, the Pearson correlation is going to be represented by rho, and in a sample, lowercase r. So you'll often see Pearson correlation referred to as Pearson's R. We're going to label one variable as X, the other variable as Y, and we're going to end up with correlation values or R values that can range from -1 to 1. And that's the complete range of Pearson correlation figures. So if you do a calculation of a Pearson's R and you end up with 5.2 or 2.3, something has gone wrong. The correlations can only be between -1 and 1. Okay, what else was I going to say here? So the two variables X and Y, we are going to be looking at covariability, right? Or the ways in which X and Y vary together. That is essentially what a correlation is. And that also speaks to the formula a bit. So again, R, Pearson's R, is the figure, the value that we want to get to eventually. And before we really get into the computations for R, which is called the correlation coefficient, we need to understand the sum of products of deviations, okay? So this is abbreviated with SP, and we're going to use SP to calculate R. So I'm kind of backing up for a bit. I'm not even going to show you the R formula yet. So SP, or the sum of products of deviations, is very similar to sum of squares, right? Where sum of squares was used to measure variability for a single variable, if you remember. We would take the sum of squared deviations where one value minus the mean, right? That would be the deviation, and then we would square it and add those up. So sum of squares was used in all of our previous test statistics. With correlation and Pearson's R, we're going to be using sum of products of deviation. Pretty similar concept. We're going to use it to measure the amount of covariability between two variables. Again, covariability. How do those two variables vary together? And the definitional formula is here, sum of products of deviations. It is exactly what it's called, what the title suggests, right? So the deviations, x minus mean of x and y minus mean of y, how much does each data point using x and y vary from its mean? So there's the deviation. Sum of products, because you multiply this deviation and this deviation, so your x deviation and your y deviation get multiplied, so that's a product, and then you add those all up. So it's the sum of products of deviations. So here, breaking it down, you're going to find the x deviation and the y deviation for each individual, find the product of the deviations for each individual, and then add all of those products up. So here is an example. We've got a sample of 4. The first person here has 1 class and spends 3 hours studying. So number of classes is what we're going to plot on the x-axis. The hours spent studying is our y variable. We'll plot that on the y-axis. First thing you're going to do is find the deviations, right? Or actually, excuse me, the very first thing you do if it's not provided for you is calculate the mean for x and the mean for all the y values. Then you would find the deviations for each individual. So you're going to take this particular x1 minus the mean that you find, and this particular y3 minus the mean of y's that you find. Then you would multiply those two things together, and then finally add all of those values up, add the products. Okay, so you may want to pause the video here and just fill in those values on a piece of paper for yourself. Pretty straightforward, easy computations. And then start the video again, because on the next slide, I'm going to fill in this table. Okay, so here we are. Calculated the mean of x's to be 3 and the mean of y, so just the average of these values here, to be 5. And so I'll do the first one with you. 1 minus 3 is negative 2. Y here, 3 minus mean of 5 is also negative 2. Then you're going to multiply across. Negative 2 times negative 2 is 4, a positive 4. And you would do that for each of the other values or individuals, and you would add up these products. So 4 plus negative 1 plus negative 1 plus 4 equals 6. So in this example, the sum of products of deviations is 6. That is the definitional formula, in which again, might be familiar when we talked about sum of squares, right? We had a definitional computational formula. When you're thinking about what the sum of products means, this definitional formula should make sense to you, right? If the sum of products is the sum of two different scores, it's the sum of products of differences or deviations, right? Um, it does get a little bit tricky using that formula if the mean of x or mean of y is not a whole number, as you can imagine, right? When you're taking every value of x and y and you're subtracting the mean, and if that mean has several decimal points, even if you round, it becomes a little cumbersome. So there is a computational formula that can just be a little bit easier to use in calculations. And this computational formula, excuse me, should give you the same exact value for the sum of products. So the result is exactly the same. They did some algebra, and this formula is a little bit easier to use. Just as before, when we had both the definitional and computational formula, you may use either one, and you'll be provided with both on the formula sheet. In this formula, n, as before, is the number of total subjects or pairs. So you don't add up what's the number of x's and the number of y's. You add up the total number of subjects or pairs of data. So here is a computational example where, again, we have the same 4 individuals. And so n here is going to be 4, not 8, because there are 4 pairs of data or 4 individuals where we are measuring 2 different variables, right? I think, what was this? Hours of study and grades, I can't even recall. Or no, number of classes and hours of studying. So you have participant 1, 2, 3, and 4. So n is 4. Again, I would suggest pausing the lecture here and then filling in these values, doing the calculations yourself just for practice, and then restarting and making sure you got everything correct. I will also take this opportunity to say that for those of you who are not reading the text before lectures, I actually think that's okay. My strategy, if I was to be taking this class, would be to watch the lecture. I try to give a pretty good introduction to these concepts, and you may find it easier to watch the lecture, then go to the textbook, read it, at least skim it, use it as reinforcement to the things that I've talked about in these lectures, and just make sure that everything makes sense to you. Okay, so here is that computational example filled in. You'll notice you're going to sum up x, you're going to sum up y, so sum of y here should be 20. Then you're also going to multiply across. So for this column here, x times y. X times y, 1 times 3 is 3, 2 times 6 is 12. And then you're going to sum up x times y. So adding down in all 3 of these columns, the sum of x times y is 66. And then you're going to simply plug these values that you calculated into the computational formula. The sum of products is equal to the sum of x times y, which we calculated to be 66, minus sum of x, which we calculated to be 12, sum of y, which is 20, divided by n, which I said in this example is 4. And you just do the calculations and you get to 6, which is exactly what we got using the definitional formula. Okay. So back to calculating R, now that we've talked about sum of products. The Pearson correlation, or R, represented as R for a sample, is a ratio of variability. So let's pause and say that again. The Pearson correlation is a ratio of variability. So we're going to have one thing divided by another to get a ratio. The sum of products measures the covariability of x and y. So how do they vary together? That's how, that's why with sum of products, we are adding the products, right? How does the variability of X and the variability of Y multiplied together, what is the measure of that? Now we need to know for our denominator, in our ratio, Pearson's ratio, how much do X and Y vary separately? And so the variability of X separately is measured by computing sum of squares for the X scores. And that will tell us how much does X vary on its own. And the variability of Y, similarly, is measured by computing the sum of squares for the Y scores. And these figures all together, the sum of products, which measures covariability of X and Y, and then sum of squares for X and sum of squares for Y, gives us our formula for R. Without further ado, here it is. So let's calculate R for our example. Here is the R formula. So sum of squares, this formula should be very familiar to you. The sum of X squared minus the sum of X squared divided by N. Remember to pay particular attention to the parentheses, right? So here's our table of data. I've added some columns here. So we have our original X values, 1, 2, 4, and 5, our original Y values. Remember, X is number of classes and Y is the number of hours studying. Added a column for X squared and added a column for Y squared so that we can more easily calculate the sum of squares. So 1 times 1 is 1, 2 times 2 is 4, and so on and so forth. That's where you're getting X squared and Y squared values from, and then you're going to add coming down each column, right? So the sum of X is 12, sum of X squared is 46, just by adding these 4 numbers together. And similarly, add down for the sum of Y and the sum of Y squared. And then you can plug in those values calculated down here in this table to the sum of squares formulas. So that's what I've done here. Sum of squares X is equal to sum of X squared, pulling that directly from the bottom of column 2, 46, minus the sum of X, 12, squared, divided by N. Again, N is 4. That equals 46 minus 36, which equals 10. Calculate sum of squares Y, doing the exact same thing for the Y columns, and you get 10 also. And then for R, using this formula here, you take the sum of products, which we calculated both using the computational and the definitional formula, and we calculated sum of products to be 6. So that's where this 6 is coming from right here. 6 divided by the square root. I'm sorry that line is missing, but it's the square root of sum of squared X over sum of squared, or excuse me, sum of squared X times sum of squared Y. So we plug in our 10 times 10, and that would of course equal 100. The square root of 100 is 10. So 6 divided by 10, and you get an R finally of 0.6. 0.6, what does that mean, right? Is that good, bad, strong, weak? What does 0.6 mean? Here is a way of interpreting or describing your R value. You'll notice this says there are no true conventions for R. So that just means there's no like absolute black and white answers. Generally speaking, a value for R between 0.8 and 1 is considered strong, whether that's positive or negative. So if you had an R value of negative 0.95, that would be a pretty strong negative correlation. And similarly, positive 0.95 would be a pretty strong positive correlation. You'll notice on this graphic that the R values can range from -1, like I said, all the way to zero point 0.1. That's the full range of R values. And at either end are the strongest values. So -1 would be the strongest. That would be a perfect negative correlation. And +1 would be a perfect positive correlation. And hopefully you'll remember I said that is extremely unlikely in the real world. So any value between 0.5 and 0.8 is considered pretty moderate. That's a pretty decent correlation, negative or positive. And then values from 0 to 0.5 in either direction is considered a weak correlation. So we calculated our R to be 0.6, positive 0.6, and that would be a pretty moderate positive correlation, right? It would go right here, 0.6. So let's do a quick learning check. Scatter plot shows a set of data points that fit very loosely around a line that slopes down and to the right. Which of the following values would be closest to the correlation for these data? So if you had which one of these R values would describe, or which R value would fit with this description of data? So fits loosely around a line that slopes down and to the right. So the first thing to remember is just kind of to picture in your mind a line going down and to the right. And you should hopefully remember that that would be a negative correlation. So we're looking at choices C or D. And when it says that the data points fit very loosely around a line that slopes in that direction, which of C and D, which is the weaker relationship? And remember, the closer you get to 1, -1 or +1, the stronger the relationship. So in this case, answer D would be a weaker relationship. So if you have a scatter plot that shows a set of data points that fit very loosely around a line going down and to the right, it would probably be something close to -0.35 versus -0.75. Okay, so just like we test or we're interested in testing the difference, whether a difference between population means is significantly different from 0, we're also interested in testing whether a correlation is significantly different from 0. Sometimes we could end up with a correlation that is clearly not 0, like the sample data we just calculated, the correlation was 0.6, but it still may not be significantly different from 0. And why is that? Just like any other test statistic or sample statistic, correlations are subject to sampling error. We are still, even though this is different, we're not measuring group differences, we're measuring we're measuring variable relationships. We're still using samples to try to make inferences about a population. And so correlations are still subject to sampling error. And small samples may have more variability, so we may not be as confident in the results, right? Just like the other hypothesis tests that we have done, the larger the sample size, the better, right? So how large would we expect a correlation to be simply because of sampling error? And how do we know whether a correlation is far enough away from 0 to call it significant? So we can compute an R value and we can describe it as weak or moderate or strong, the correlation that we find. But how do we know whether we're seeing a strong or moderate relationship because of the relationship between the variables, or what part of that is sampling error and not really reflecting a relationship at all? And the answer is hypothesis testing, right? So this should be very familiar to you. This is the exact same concepts that we've talked about with t-tests and ANOVAs. What are the null and alternative hypotheses? Recall that rho is the population value for the correlation. So in the population, the null hypothesis would say the correlation between the two variables is 0, right? And the alternative or alternate hypothesis is that the correlation is not 0. Remember, if the correlation is 0, that means there's no relationship. That's the very weakest relationship. It's the absence of a relationship. If the correlation is not 0, meaning there's some relationship there, that's our alternative hypothesis. And you could have directional hypotheses about correlation as well. So this set of null and alternative hypotheses is for a two-tailed test, right? In the population, the correlation is not 0. We're not saying whether we predict the correlation to be positive or negative. We're just saying it's not 0. There will be some correlation, right? Just like before, where the null hypothesis was no effect, here the null hypothesis is no relationship. The alternative hypothesis is that there is a relationship, or that the correlation is not 0. We are not going to do directional tests in this class this semester, but it is possible to do directional tests, hypothesis testing with correlations. You will be glad to know we can use the t-distribution to test the significance of correlations, to test whether we should reject or fail to reject the null hypothesis. We have to use a slightly different formula for t because we're looking at correlations, not differences. And remember back to the central limit theorem that any population parameters sampling distribution tends to be normally distributed. Okay, so after we've stated our hypotheses, the second step in hypothesis testing with correlations is to determine the critical value. So remember, we're going to be using t-statistic that you guys should all remember and be very familiar with. We're like I said, always going to be using a two-tailed test for this class. Just remember that in the real world, beyond this class, you need to have a very good reason for doing a one-tailed test. And for our example, we're going to set alpha at good old 0.05. And what will our degrees of freedom be? So we have 2 samples. Our degrees of freedom will be n minus 2. And remember, for correlations, n is the number of pairs, or the number in each sample. And each sample is a little bit misleading. It's also like the number in each set of data points. So you've got X and Y, right? When we say we have 2 samples, we're meaning we're measuring 2 data points for each participant, or we have 2 variables that we're looking at. And so we have pairs of data. So what's the critical value for our sample with number of classes and studying? Let's return to that example. So, goodness, that is not a good font color. Hopefully you guys can see that. The degrees of freedom, we had 4 pairs, remember? So degrees of freedom is 4 minus 2, which equals 2. So we're going to use 2 degrees of freedom, and we're going to be looking at this row. We said that our alpha two-tail tests, so we're going to be looking in this part of the table, and we set our alpha at 0.05. So we're going to need to look at this column. And so our T critical is plus or minus 4.303. So finding T critical is just a matter of looking in the T table. And then step 3, computing our test statistic, or T obtained. So our T formula is sample statistic minus population parameter divided by standard error. This should be really familiar to you guys. Oh, I've got a baby who is awake. Hang on just a second, guys. Okay, sorry about that. All right, so we've got our T statistic. In this case, the sample statistic is R. Wow, can you guys hear that train horn? All sorts of interruptions this evening. The population parameter is rho, and our standard error formula is here. The standard error for R is the square root of 1 minus R squared divided by n minus 2. So here's what our T test statistic equation looks like down here in the bottom right of this slide. So sample statistic R minus population parameter rho divided by standard error. Pretty straightforward, and again, you'll have these formulas on the formula sheet in addition to your textbook. So, oops, I'm sorry that that's showing up now. Going back to our example, we calculated R to be 0.6, if you recall, and N was equal to 4. There were 4 pairs of data. And so we'll calculate the test statistic using the formula. T is R. And this should be R, excuse me, this should be R minus P divided by the square root of 1 minus R divided by N minus 2. And R minus rho is going to be 0, right? So just like the other hypothesis testing that we've done, the population parameter is set to 0 because we're assuming that the null hypothesis is true when we're calculating the test statistic. So pause the slide, plug in all the values that we've already calculated to compute T. And you should end up with a T of equal to 1.06. And then step 4 in hypothesis testing is make a decision, right? So we looked up in the table the T critical value plus or minus 4.303. We calculated T to be 1.06. What should our decision be? It should be pretty straightforward. You'd report it this way: T with 2 degrees of freedom equals 1.06. The p-value is greater than 0.05 here, so we would fail to reject the null, right? Our T obtained is not in the critical region. Because 1.06, our T obtained, is less than 4.303, our T critical, we fail to reject the null hypothesis, that should say, and conclude that there is not enough evidence to suggest that the correlation between number of classes taken and number of hours studied differs significantly from 0. So the correlation that we found, what that means is that it could be due to sampling error, or we just may not have had a large enough sample to pass the critical value cutoff. And so the best thing to do in this case is collect more data. Again, this should say we fail to reject the null right there. I apologize for that typo. Effect size. So just like with the other test statistics we've done, we will calculate effect size. A correlation coefficient measures the degree of the relationship between two variables on a scale from 0 to 1, right, in both negative and positive directions. We can square that correlation coefficient and use the resulting value to measure the effect size. In this case, how much variance is accounted for by the relationship. And we're going to call this value, squaring the correlation, the coefficient of determination. So you might recognize R squared from ANOVA. For example, if we computed R to be 0.71 for the relationship between money spent on junk food and money spent on organic food, that would mean that 50% of the variability in money spent on junk food can be explained by the relationship between organic food and junk food purchases, or vice versa. And where is that 50% coming from? If you take 0.71 and you square it, you get 0.50. And there's where I'm getting 50%. So to compute R squared, you just square your R value. And then we can interpret R squared, or the coefficient of determination, as indicating how much variance is accounted for by that relationship. So here, 50% of the variance or variability in money spent on junk food can be explained by the relationship between spending on junk food and organic food. And just like before, if you get a non-significant result, if you fail to reject the null hypothesis, you don't need to go further and look at or compute or interpret effect size. You only want to know the size of an effect when you have a significant effect, right? If it's not significant, it doesn't really make sense. Here's another way of looking at that interpretation of R squared. So another way to say it is that the shared variance is equal to 50%, and that was what R squared equals. So you might think of it this way. This big gray circle is the total variability in money spent on organic food. The lightest gray circle is the total variability in money spent on junk food. And our correlation of 0.7 means that 50% of the variability in these two things is due to the relationship with each other. So this is kind of a neat way to think about what does correlation and the coefficient of determination mean conceptually. Okay, let's do a few learning checks. True or false, a set of n equals 10 pairs of x and y scores has sum of x equal to sum of y equal to the sum of x and y is 20. For this set of scores, sum of products equals -20. And that answer is true. Sorry, I probably should have given you more of a break there to compute it on your own. And that's just plugging numbers into our formula for the sum of products. So go back to your formula, plug in the numbers that are given in this question, and you should come up with the easy answer here, -20. If the y variable decreases when the x variable decreases, their correlation is negative. True or false? I'll give you a second there if you want to pause your video. This is false. So to the extent that I ever give you guys a trick question, this is kind of it. Like I mentioned at the beginning of the lecture here, when each variable decreases together, it may sound like that is a negative relationship because y variable decreases and x variable decreases. But remember, when the variables change in the same direction, whether that direction is positive or negative, that indicates a positive relationship or positive correlation. So if test scores go up as income goes up, they both move together in a positive direction, that's a positive relationship. If they both move together in a negative direction, that is still a positive relationship. The key is, as one variable goes up, does the other go up? As one variable goes down, does the other also go down? If they're both going in the same direction, that's a positive relationship. Okay. Note of caution. So remember, I mentioned before, correlation does not give us evidence of causation. Just because two variables are related to one another, or even if one variable can be used to predict another variable, that does not mean they cause one another. This is super duper important. And just a preview, when you're using one variable to predict another variable, that's regression, and we're going to talk about that in the next lecture. But neither correlation nor regression means causation. So maybe X does cause Y, maybe Y does cause X, or maybe there's some third variable that causes both. And how can we find, let's say we're looking for evidence of causation. And first, I'm going to try to share a different screen here. Let me see if I can do this. Okay. So here is a really neat website. You can see the web address in my slide and here on my screen. So this is a website that somebody came up with showing spurious correlations. Spurious means it appears that two variables are highly related to each other, and they are related or correlated with each other. But spurious meaning there's clearly another variable or more than one other variable that's truly causing the effect. So here, I'll give you an example. This is a really good one. Number of people who drown by falling into a pool correlates with films Nicolas Cage appeared in. And if you look at this graph, it is a little bit startling how these two variables go together. And you'll see a computed R value of 6.66. So a pretty moderately strong correlation. And the graph would reflect this as well. But I think most people would agree there's absolutely no causation in terms of people who drown with and the number of films that Nicolas Cage has appeared in, right? Or cheese consumption and death by becoming tangled in your bed sheets. Divorce rate and consumption of margarine. So these are really outlandish examples, all to demonstrate Let's go back to our slides. All to demonstrate that correlation does not in any way give evidence of causation, right? It's pretty obvious that those things listed on the site, while they perhaps do relate to each other, they certainly do not cause each other. So hopefully that will just help you remember that that is the case. How do you find evidence of causation though? So let's say you've got two variables, you've got a strong correlation, you do think that X causes Y, for example. How can you figure that out? Recall, oops, excuse me. You will learn a little bit about that in research methods, which is another class that hopefully most of you will be taking or have in the future. And evidence of causation requires experimental manipulation and all sorts of other things. People need to randomly be assigned to conditions, and there needs to be a manipulation of the independent variable. Remember, with correlation, we are almost always observing two variables as they exist. We are not manipulating them in any sense. So number of classes and number of hours studying, for example, we're not randomly assigning people to take a certain number of classes. We're not manipulating either of those variables in any way. And so what we end up measuring is purely correlation, not causation. Okay, some other things that affect correlation measurements, or Pearson's R, and these are really important things to be aware of. One is restriction of range. So this is important because the way that data can be cherry picked is a term you may have heard or will hear, to look like there is a stronger or weaker correlation than there is. So if you look at, let's just say that we're looking at a particular test score, and this may be SAT scores or something like LSATs or GRE scores, and then GPA. And if you don't include the full range of possible scores, then you're going to be looking at distorted data. So let's say that in this case, the full range of test scores is from 200 to 800. That's the full complete range. You can't get lower than a 200, can't get higher than an 800. If you were to calculate an R value or correlation coefficient for just the range of scores that ranged from 400 to 800, these are the scores you'd be looking at, and your R value would only be 0.43. And so you would inaccurately report that there is a weak correlation between these two variables, GPA and test scores. And that is the problem with restricting the range. When you include the full range of test scores from 200 to 800 and you compute an R value, you see up here the R is 0.65. And remember that that would be considered a moderately strong positive correlation. And so you can see, hopefully, that if you restrict the range, you end up with a very different value, a very different interpretation of the data, and one that could be, in some extreme situations, absolutely incorrect. So it is never a good idea to restrict the range in either variable. You wouldn't want to just look at GPAs that were above 2, right? It would just present a very distorted view of actual data. Another factor affecting Pearson's R is outliers. And this is a really good example. Your book gives another really good example, so take a look at your textbook as well on this one. Extreme values can affect the correlation. So here we've got expenditure on tobacco and expenditure on alcohol. So and the line that we can draw through these data points indicates a positive relationship, right? Not super strong, but the as you spend more on tobacco, the spending on alcohol also goes up. If you include Northern Ireland, however, which is this data point right down here, and your calculations, you would get an R of 0.224 and a p-value of 0.5. Now remember, p-value 0.5 means definitely not significant in terms of hypothesis testing. And so you'd say there is no relationship between these two variables, right? And the R would be 0.22, which is very weak. Let's say we take Northern Ireland out because we identify it as a clear outlier. Now we've got an R of 0.784, which is quite a strong relationship, and a p-value of 0.007. So definitely significant in terms of hypothesis testing. Given that result, we would definitely reject the null and say there is a clear, strong, positive relationship between expenditure on tobacco and expenditure on alcohol. In this case, removing an outlier doesn't falsely manipulate the data. When you find an extreme value or outlier, it's the responsible thing to do to remove it and to look at the relationship with that particular data point excluded. Now you would want to report that in your results, and maybe say this correlation for all the countries except for Northern Ireland indicated a very positive, strong relationship. But you wouldn't include Northern Ireland in your statistical evaluation because it is such an outlier. And so it's important to remember that outliers have a pretty good extreme effect on Pearson's R. We kind of like outliers affect the mean, right? They really pull the mean in one direction or another. Okay, using and interpreting Pearson's R, as we will see with the next lecture, which is the second half of chapter 14, Pearson's R does allow us to predict one variable if you know the other. Again, that does not mean that they cause each other, but if we have a very strong relationship, then the value of one variable can help us predict the value of the other variable. This is called regression, and we'll talk about that in the next lecture. Also, validity. Validity allows us to compare two scores that theoretically should be related positively or negatively. So your book talks about these interpretations of Pearson's R. Basically, with validity, an example is, let's say we create a new assessment or measure of depression, right? A 10-question quick scale for depression. And when we're testing our new measure or new scale, we would want the scores on our scale to be correlated significantly with some other measure of depression that is already existing, that we know is a really good measure of depression. And so a lot of times people will use Pearson's R and correlation to tell, does my new measure work? Is it a valid measure of whatever it is I'm trying to measure, right? Similarly, reliability. So we can assess the extent to which a measure produces stable, consistent measurements. If my new measure of depression, my 10-question depression scale, is a good measurement tool, then it should produce stable, consistent results, right? If you take my measure today and you score a 2, later today you should still score a 2, right? There should be a strong correlation between scores at one time and scores the next. And so reliability is another factor that is often using correlation or Pearson's R values to um, measure reliability. Sorry, I'm not really explaining this very well. And side note, pet peeve, I know some of you might be familiar with the Myers-Briggs personality test or personality assessment scale. They yield 16 different types, and they are not good in terms of reliability. You can take the Myers-Briggs and score very inconsistently. Your score on one time taking the Myers-Briggs would not correlate or have a strong relationship with another time taking it. So not so great reliability. Okay, and then finally, theory verification. So correlations and Pearson's R can help us validate theories that say two variables should be related. So there may be a theory, for example, that says depression is very related to rumination, right? There's a cognitive theory of psychology that says those two things go together. People who tend to ruminate on negative thoughts tend to report higher depression scores. And at first, that was just part of a theory to explain part of depression. And you could verify that part of a theory using correlations. You would want to measure. Okay, guys, I'm not really sure what happened with my video, and I'm hoping it didn't erase my whole recording. I'm going to talk about technical difficulties. I know a lot of you guys have been having those yourselves, so I get your frustration there, 1000%. Okay, I was talking about theory verification, and these are prediction, validity, reliability, and theory verification are always really useful ways of using correlation. So even though correlation is limited in that it does not indicate a causation relationship, it can be really useful in other ways. Okay, alternatives to Pearson's R. So remember, one of our objectives was to talk about alternatives. The Pearson correlation, again, was developed for data with linear relationships. If it's a curvilinear or some other kind of relationship, you cannot really use Pearson's R. And remember that Pearson correlation was also only to be used with data from interval or ratio measurement scales. They have developed other correlation measures for data with nonlinear relationships or data from nominal or ordinal measurement scales. So one alternative is the Spearman correlation, and this can be used with ordinal variables. Remember, ordinal is rank order. So when you can say, I finished first, second, or third place in a race, the difference between first and second and the difference between second and third places are not necessarily the same. You may not even be able to measure them necessarily, but you still can put them in a rank order. And so variables like that, when both variables are measured on an ordinal scale, you can use the Spearman correlation. You can find the correlation between two variables that have a monotonic but non-linear relationship. I'm not going to go into a lot of detail about the Spearman correlation. What you'll want to know is that it can be used, it's an alternative to Pearson's R, and it's a type of correlation, and it can be used with ordinal variables. Okay. And then another alternative is the point biserial correlation. This is used when one variable has only two values or levels, and the other variable is an interval or ratio variable. So let's say that you're doing income and work from home versus work at work. okay? Um, your work location variable is dichotomous, meaning it only has two values or levels, right? So in this case, do you work from home or do you not work from home? Yes or no? The other variable, income, would be an interval or ratio variable. And so in that case, you can't use Pearson's R, because remember, both variables would need to be interval or ratio measurement scale variables. But you could use a point by serial correlation. It's very similar to doing an independent samples t-test. In fact, if you test the same data with an independent samples t-test and point by serial correlation, you should get the same effect size and significance. And with a point by serial correlation, you get, or excuse me, you can also use the phi coefficient, which is used when both variables are dichotomous. So maybe you want to look at whether people working from home have kids or not. So work from home, yes, no. Have children, yes, no. Both of those variables are dichotomous. Is there any relationship between people who work from home and whether or not they have children? You could look at the correlation there, the relationship between those two variables using the phi coefficient. So you might see a question on the exam that presents a hypothetical research question like that. Like, is there a relationship between people who work from home or not and people who have children or not? And I might ask you, which correlation measure would you use for that research question? And you want to be able to identify, okay, those are both dichotomous variables. I would use the phi coefficient. Okay, lastly, a few learning check questions. Participants were classified as morning people or evening people, then measured on a 50-point conscientiousness scale. Which correlation should be used to measure the relationship? This is exactly what I was just talking about. This sort of question is one you might see on the exam. I'm just pausing in case you want to try to answer the question before I give it to you. Point by serial correlation, right? Because one of the variables is dichotomous, morning people or evening people, and the other variable is interval or ratio, the conscientiousness scale. Okay, true or false? The Spearman correlation is used with dichotomous data. Pause for a second. And that is false. And you again just want to remember that the Spearman correlation is used when you have ordinal or ranked data. True, false. In a non-directional significance test of a correlation, so that should tell you two-tailed, right? The null hypothesis states that the population correlation is 0. True or false? And that is true. The null hypothesis assumes no relationship, right? Just like the null hypothesis assumed no effect when we were talking about t-tests and ANOVAs. Rho equals 0 indicates no relationship in the population. All right, that is the end of chapter 14, the correlation section of chapter 14. There will be another separate video for regression. Thanks very much. Please let me know if you have any questions.